Welcome back to Series 3 of the Atari ST Nostalgia GFA Basic Tour. In the last video we went through the functionality of BitBLT step by step in a 3-part mini-series. And at the end, our result actually got a little bit faster even, and I want to take that result as our starting point for these videos and then explore how we can actually further boost the performance of our sprite routine, because believe me, it can get quite a lot faster. And stuff is going to get a bit more advanced here, so again this will be a 2-part mini-series. And in this first part I will try to explain the theory as best as I can, and so we can then use part 2 to actually apply this acquired knowledge to our sprite routine. And I'm first going to show where we left off in the last video, which is the BitBLT sprite animation. And I'm going to just start it, because remember we timed it, and I already mentioned in the last video it took like 10.5 seconds for a complete 360 step loop, which means not every step is yet within 2 vertical blanks. And this is like between 10.5 and 10.6, it depends a little bit. But this number, this 10.5, means if we calculate, suppose we wanted to have every animation step within 1 VBL, so 360 step with 1 vertical blank per step. And remember, in Monogram 1 vertical blank is like 71.49 Hertz or something. So if we divide 360 by 71.4 something, we will get like 5.0.5. Which means if every animation step would take about 2 vertical blanks, the time would have been 10.09. But the actual time it took for 360 steps is 10.5 seconds. And that is actually quite interesting, because that means not every step is finished within the time that takes for 2 vertical blanks. But if every step will take longer than 2 vertical blanks, the loop would actually take 15 point something seconds, because it would be like 2.1 vertical blanks, but I would wait for the next one, so every step would be 3 VBLs. So that means there must be a difference between our steps inside the animation, and that is actually quite interesting. And I'm going to just load the code for the video that I will need earlier. And that's actually quite interesting, because that means there is a time difference between our steps, where some take longer than 2 VBLs. And the steps are basically all the same. I mean, the calculations and variable reads, they are all the same for every animation step. So we can suspect that the difference is coming from the execution time that the BitBLT commands are actually taking for each step. And so how can this be? Because the only difference in each step is actually the actual coordinates that the sprites are drawn on, and that is indeed what affects the performance. And I want to try to explain it as best as I can, and I made some visualizations again. Because remember, graphics are just bytes in memory. It's just a byte value, a value that I write, and the shifter takes these bytes, or maybe word by word even. There's like words in screen, like word values, which is 16 bits, and it reads them and puts them on screen. It also means, in this example, I have my 16 by 16 pixel sprite, and each line of my 16 by 16 pixel sprite represents one word value, so one 16-bit value. And in this example, I've put the sprite in the screen, and the most significant bit of my sprite image is actually fully aligned with the most significant bit of the word value in the screen. So my x-coordinate, like in my sprite buffer, it starts at 0, 0, and the next one was at 32.0. It can be at like 160.0. So they're all perfectly aligned. So it's really easy to pick up these values and write them somewhere else. However, what happens if I shift the sprite by 4 pixels? Then a lot more is going on. Because now the most significant bit of the sprite is now somewhere else. It's shifted by 4 pixels, my image. Which means the most significant bit of my sprite and the least significant bits of my sprite is no longer aligned with the least significant and most significant bits of the word value on screen. And which also means the command I use to put it on screen, it just cannot write the values. It must sort of shift these bits around. Or it must like apply the new data bit by bit on this area, and it also has to operate within 2 word values of the screen memory instead of 1, because it's shifted. The right part of the sprite is actually in a new word value, in a different word value than the other one. And the BitBLT command always sort of have to assume the worst, because it has to work always in every situation. So it will always treat this as a bit by bit operation. I mean, it's a bit operation. But what if we could just write the new graphics, but we always make sure that where we write it to, the values are always word aligned. So the 16 bits in my values that I write are always aligned with the 16-bit values on the screen memory that I read from and that I write on. So it will probably stay a lot faster. And the good news is, yes, we can, but it has some consequences, because now, because my most significant bit always has to be the same as on the screen, so that is sort of fixed. It means my area that I have to write, because I have to start all the way to the left where that green dot is, the area that I have to write now is 32 pixels wide instead of 16 pixels wide. So it's a 32 by 16 sprite instead of a 16 by 16 sprite. Because we have to stay aligned. And of course, to be able to have a single pixel movement horizontally, we need a copy of the sprite that is already shifted before we put it on the screen. And this option 2 is actually quite easy, because we have already done that in part 34. We did it with whole screens that was shifted by 4 pixels. And we can do exactly the same with smaller areas. There's absolutely no problem in that. And option 1 is also not too hard in principle, but it will only make sense if the command we use for that, for using this aligned 32 by 16 sprite instead of the shifted 16 by 16, it has to be much, much faster. And that means we have to do some performance testing and try out different options. And those are the options that I'm going to, sorry, I have to go to my editor screen, that I'm going to test with this code. As you can see, I'm doing a 16 pixel wide blit of an object. Then the same with 32 pixels. I'm doing card long, which I will explain, do something for a big object, and also do some measurements on the bmove command. And basically the 16 pixel blit is what we have done already. So I'm going to do a word aligned. I'm going to take a 16 by 16 pixel, which will just be the small ball with the Atari Fuji logo in it, and put it at an x coordinate of 320, which is a multiple of 16. So this BLT command will put it, and it will be word aligned. And then I'm going to do the same, but instead of word aligned, it's going to be shifted by 7 pixels. So the x coordinate will be 326 instead of 320, 0. And of course, each command I'm going to do 5,000 times to make a nice measurement. And I'm going to measure it including the for next loop. So the measurements will be a bit skewed, but you can see the difference pretty quickly. So you can see that they are actually different in performance. And then, of course, if I want to replace the 16 by 16 shifted sprite, I have to replace it with a 32 pixel wide, so 32 by 16 word aligned sprite. So that's what I'm going to do here. The bit BLT command, I just take different source dimensions in the array for the bit BLT command, and then I'm going to blit that 5,000 times to see if this one is faster than the shifted 16 by 16. Because if it's not, there's no use of using this one with pre-shifted sprites. And I'm going to do the same for RC copy, because who knows, maybe that one will be a little bit faster when it's operating on 32 by 16 objects. And yeah, I'm also going to measure some bmove, because I want to know if a 16-line bmove or a 30-line bmove is indeed faster than using a bit BLT or different command to put this 32 by 16 area for the cleanup. So I can operate that as well. But the most interesting ones, and those are the commands we are going to learn to operate in this series of videos, is actually using card and long commands. And what card and long do, this card command, what it does, it will write a value. It will write a 16-bit value, in this case a word value, in the address that I specify here in these curved brackets. And it means I have to know my addresses that I have to determine. Because this all looks a bit intimidating, but basically what I'm going to say, the card command, please at this address write the value after the equal sign, and the equal sign will actually be the source address, so basically the address of the source of the sprite that I'm going to get, but I want you to OR it with the original value that this address had. So this dest start plus card shift is exactly the same here, and the card shift is basically counting from 0 to 1200 in steps of 80, so I'm going from line 0 to line 15 to write 16 lines, and in this case 16 lines of 16-bit. And these addresses I have to determine because the card command is not a graphics command. It doesn't operate on pixels, it operates on even numbers of bytes. And I'm going to do the same here, but with the long command, because I want to write a 32 by 16 pixel sprite, which means I want to write 16 lines of 32 pixels, for which I'm going to use the long command, and it's the same. And to explain these commands as best as I can, remember we were already here. We wanted to write this 32-bit value. And instead of writing this whole area, like I'm going to input and output the area, I'm just going to input bytes, or in this case word and long word values, and write them below each other line by line. So it's still nicely aligned, and I still need the pre-shifted sprite. But remember, one scan line of 32 pixels in monochrome is 32 bits, which is one long word value, which this long command that I showed is 4. And if I do 16 of them from top to bottom, you basically have the image. There's, however, one thing that we need to do. As I said, it doesn't operate on pixels. So I have to calculate the word aligned byte. And so I have to convert my X and Y pixel to a byte value that I have to write. And in this case, the destination of my sprite, in this case of my image. So I want to put my image, my 16 by 16 pixel image, and the top left coordinates are the X is 36 and the Y is 100. And I have to convert that to a byte value that represents the pixel that is on the top left of this 32 by 16 pixel object, the word aligned byte. And for the Y coordinate, this is really easy because I just multiply it by 80. So 100 times 80 is 80 bytes, 8,000 bytes. So that's really because each line is 80 bytes in monochrome. So that's pretty easy. For the X pixel, I need a byte address, but it has to be an even address, which means I have to divide it by 16, ignore the decimals, and then multiply it by 2 again. So it's like the X pixel, in this case 36 div 16. So I'm using the integer division, which means 2 words, and 2 words times 2 is 4 bytes. So in this case, the address will be the buffer screen, if I'm writing to a buffer screen, or in my code it will be the logical screen address, plus 8000 plus 4. And for the next one it will be plus 8084, and then 8164, etc, etc, etc. So it looks really complicated, but it's just recalculating pixel positions into byte positions. So it's not as hard as it looks. It's just something you have to be really careful about and don't forget. And in this case, in my sprite buffer, my sprite is actually at coordinates 0.0. So my byte source address is actually sprite buffer plus, the rest I don't have to calculate. And for my destination, it's a bit more complicated, but as you can see, I'm writing to my logical screen plus the X coordinate, which is 336, divided by 16, and that number is then multiplied by 2. So now I have the nearest word aligned byte. And of course I have to add the Y coordinate, the right scan line to it. So I'm going to add the multiplication of 192, which is the Y coordinate, times 80. So basically it's x divided by 8 plus Y times 80. But I have to make sure it's actually an even address. So that's why I divide by 16 using an integer division. So it will ignore the decimal values and then multiply it by 2. Because if I get an odd address, the long command will fail because it needs an even word. So the long command and the card command both require a word aligned byte address, which is not a problem because that's what we wanted in the first place. So I hope I explained the commands as best I can. Because now I want to do the measurement, and to do this measurement I have to run this program. And don't mind too much about what's happening on screen. It's just I put a background to show that it's actually transparent, but it's not what's happening on screen. It's actually the commands I'm executing and the measurements I do. And what I'm going to do, because I know in the interpreter actually this takes a really long time. So I've now set my emulator to go fast forward as fast as it can, so we can see the measurement results. So you really quickly saw the B move happening there, and I'm going to set it to normal speed again. And these are the results in the compiler, and there's several conclusions we can do. The first thing we see that the shifted 16 by 16 sprite is indeed a lot slower than the 5000, than the aligned 16 by 16 pixel sprite. So you can see that if you want to do something with only vertical movement, it's actually best to always do it 16-bit aligned. Because you can see even if you use RC copy or anything, it will still be faster. And of course, if you want to do this aligned 32 by 16 pixel sprite to speed up the process, we can see that actually in the bitblt command, the 32 by 16 pixel sprite takes longer than the shifted 16 by 16 sprite. So this command is not going to help us in further boosting our performance. And the same goes for RC copy, which is even slower, as you can see, quite a lot slower even. So those are sort of out of the question. And yeah, you can see for the big logo, so 19.2 by 32 shifted or aligned 112 by 32, you can see actually there the bitblt command is already faster. So putting the logo shifted and using bitblt is actually faster than the non-aligned 96 by 32. So especially for big objects, it really pays off to put them to put them slightly, put them word aligned. What we also see is that actually the card and long listings that I showed are actually way longer. So that's a bit discouraging, but we should not be too discouraged, and because remember, these are like lots of small direct writing commands, which in the interpreter are always really slow, just like lots of variable writes, and as we saw with like these array reads and writes. But at the same time, we know that these small actions, these small instructions, actually after compiling get a lot faster. So I'm going to use the same program again, but now I am actually going to do it compiled. And in this case, I am not accelerating my emulator. So this is the actual time that it would take on a normal plain ST2. And remember, everything I'm doing is on a normal plain STF, so no STE, no mega STE, no blitter, nothing. So results might be different on different machines, but I'm assuming the plain old STFM, like I had when I was, like we had as a family computer, I must say, when I was a child. And you can see, a lot of these commands still take quite some time because, I'm doing them 5,000 times, which is quite a lot. But these measurement results and what we learned about the commands, and remember, I didn't explain the code every step by step because I will be publishing the code on my GitHub page. And along with it, I will also publish all the slides I use in my videos, so you can sort of look at them and really try to comprehend what's going on, because it really looks very intimidating, all these byte values and stuff, and this recalculating, but it's really plain simple logical steps. These are the B moves, so the 16-line B move, and the 32 is I'm basically just copying the first 32 lines of my sprite buffer, as you can see. And now we see the results after compiling, and we can see that the bitblt commands both, they all got a little bit faster after compiling, but we can still see that the aligned 32 by 16 pixel sprite using bitblt is still slower than the shifted 16 by 16 sprite, also using bitblt. So that's a bit of a pity because we cannot use that. So we cannot write something with word aligned pre-shifted sprite using bitblt and get some performance gain because the objects have to be bigger. That's something we have to live with. But what we also see, these card and long listings that were like really long in the interpreter. I mean, it was like 80 seconds or something. I forgot even, and even in the big object it was even longer. But now we can see that actually 5,000 times this 16 long listings to create this 32 by 16 pixel sprite now only takes 2.5 seconds, which is way faster than the 4.2 seconds it takes us to write this 16 by 16 pixel sprite. So using this long list of LONGWORD commands together with word aligned sprites and pre-shifted sprites is probably going to get us a lot of performance gain if we apply it correctly. So that's something I'm getting very excited about. And the same goes for the big object. We can see it's still quite a bit faster than the shifted bitblt shifted sprite, and also faster than the aligned bitblt sprite. So that we were going to use the method for both the small and the big sprites, and we can also see that actually this 32 by 16 long listing is also a lot faster than a B move of 16 scan lines. So for the small object, it's also pays to use the long command for cleanup instead of the B move. We can also see that for 32 lines, actually, it's still better to use the B move command because it's only one command and it does it boom just like that. And it's like 8 seconds versus 14 seconds for the card command. So that's still a lot faster. So we will keep cleaning up the big logo with B move, but we're going to do the small sprite cleanup with the long listing. And we are also going to animate our small and big sprite using these long listings with pre-shifted sprites. Of course, that's not what we're going to do now. This was just a theory, and the proof is in the pudding. So we did performance measurements where we actually see that, yes, this is probably going to help us in boosting the performance. So that's a lot of theory we learned, and it will help us optimize our sprite routine. And I don't want the videos to become too long because we are already close to the 20-minute mark again. So we will do it in the next video where we will apply our newly acquired knowledge to update and really give our sprite routine a performance boost. So I hope to see you in the next video. For this one, as always, I would like to thank you for watching.